Let us try to understand the Joule Thomson process or the Joule Thomson experiment. And its possible outcomes. Now, this experiment was initially performed by Joule and he came out with some result which was questioned by Thomson. Now, this Thomson is nobody other than Lord Kelvin himself, and upon his Lord Kelvin's suggestion, Joule repeated the experiment with more refined and more accurate measurmental and experimental apparatus, and hence this experiment is called as Joule Thomson experiment. The apparatus consists of a region or a cylinder divided into two compartments, say region 1 or the lower region and region 2 or the upper region, by a plug which is porous in nature. Porous plug. A porous plug is nothing but a plug having very small holes, or as we can call them pores, and it is made up of silk fiber or cotton wool material when it is compressed very highly. So it has got very small large number of pores. So basically the gas from region 1 can enter into region 2 by passing through these small pores. Now this region 1 is maintained continuously at a high pressure value, which is of course has to be kept at a constant value, and this region 2 is exposed to the atmosphere. So this is continuously kept at constant pressure but lower than P1. So let us call this pressure as P1 in this region 1 and this as P2 in region 2, such that P1 is always larger than P2. Now there are two thermometers to be used to note down the temperatures in the two regions, say T1 and T2. Typical platinum wire thermometers were used in the original experiment. So when the gas passes from this region to the other region through this porous plug, the temperatures in the two regions are to be noted down. And it was observed that there are three possibilities. Either T1 is smaller than T2, that is the gas gets cooled. So we observe a cooling effect. Excuse me, the other way around, sorry. If T1 is larger than T2, the temperature here is larger than the temperature above, then we get cooling effect. Or T1 is smaller than T2, that is the initial temperature in the region 1 is higher than the temperature in the region 2. Then we get heating of the gas or the heating effect. Or in some cases, it was observed that T1 was same as T2. So there is no change in temperature. Of course, these three possible outcomes were tried with different gases and different values of temperature in the region 1. Further, it is observed that as T1 is increased, the difference between T1 and T2 goes on decreasing. At a particular value of T1, it becomes, or it is observed that T1 is same as T2, and then no further cooling is observed for some temperatures larger than T1. That particular temperature T1, which corresponds to T1 equal to T2 and beyond which no cooling is observed, is called as inversion temperature. The theory behind these three possible outcomes has already been studied in detail, which we are going to discuss here in brief. This process, of course, all this setup of Joule Thomson experiment has to be enclosed in a constant temperature bath. Now, in order to understand these three outcomes, we must know that the process, namely Joule Thomson process, or the throttling of the gas from region 1 to region 2 is isenthalpic. That is, the enthalpy in region 1 is same as enthalpy in region 2. That is, by the definition of enthalpy, U1 plus P1 V1 is same as U2 plus P2 V2, or H is a constant. We should note that H is U plus PV, which is a constant. So if we differentiate this, we get, differentiating this, we get dH is equal to 0. Since it is a constant, its derivative has to be 0. But dH is nothing but derivative of U plus PV, since H is U plus PV, is 0. Now d of U plus PV is simply du plus PdV plus VdP, which is 0. But this du plus PdV is dq, and this dq is TdS, right? So let us call it as equation 1. Now let us introduce entropy S as a function of variables T and P. Then if we differentiate this ds, we get dou S by dou T at constant pressure into dt plus dou S by dou P at constant temperature into dP. This is how we take derivatives when derivatives of a variable when it is a function of two variables. Now if we use this equation in equation 1, we get, so for this ds we have to replace by this entire expression. So we get T into dou S by dou T dt plus dou S by dou P dP plus VdP as it is equal to 0. Now by definition, we have T into dou S by dou T at constant pressure as Cp, the specific heat at constant pressure. And we have the Maxwell's relation, dou S by dou P at constant T equal to minus dou V by dou T at constant P. So if we use these here, we get Cp dt minus T dou V by dou T at P plus VdP is equal to 0. Now if we rearrange this, so this Tp can be taken common. So we have V minus T dou V by dou T is equal to 0. This can be rearranged to get an expression for dt by dP, how the temperature changes with change in pressure. And it is equal to 1 by Cp into T dou V by dou T minus V. We note that these This ratio on the left hand side is important because for the two regions, the pressure here is P1, the temperature here is T1, whereas the values are P2 and T2 on the other region of the porous plug, the other region separated by the porous plug. This dt is just T1 minus T2 and dP is P1 minus P2. So this ratio of dt by dP is going to decide whether the gas is going to cool or heat or no temperature change is observed. So this dt by dP is denoted by letter mu, and it is called as Joule Thomson coefficient. We should note that dP is always positive. Why? Because P1 is larger than P2. So if we need to have dt to be positive, that is T1 larger than T2, that is cooling effect, we need to have the right hand side to be greater than 0. So whenever for the given gas, the right hand side, the term on the right hand side of this equation is greater than 0, we are going to observe cooling effect. So if dt is less than 0, that is T1 is less than T2, or we observe heating, the right hand side is going to be less than 0. Similarly, for the inversion temperature, which corresponds to no change in temperature, or T1 is same as T2, the right hand side is to be equal to 0. That is, for the inversion temperature, T into dou V by dou T at constant P minus V has to be equal to 0. Now, the only task is to determine the value of this quantity in square bracket for the given gas. And we see that if the gas is ideal, that is, we have PV is equal to RT, PV is equal to RT, or V is equal to RT by P, we get dou V by dou T at constant pressure to be equal to just R by P, right? So T into dou V by dou T at constant pressure is going to be T into R by P. So this minus V is minus V, and T into R by P is V minus V is equal to 0. So this factor in the square bracket is 0 for ideal gas. So for any ideal gas at any given temperature, dt by dP is always going to be 0, or dt is also going to be 0. So if the gas is ideal, we see that no effect of cooling or heating is observed. There is no change in temperature. But if the gas is a real gas, that is, instead of PV is equal to RT, the gas obeys the van der Waals equation, P plus A by V square into V minus B is equal to RT. In this particular case, by doing some simple algebra, which may take sufficient enough time, we see that this quantity V into dou V by dou T at constant P minus V, that is the quantity in the square bracket itself, comes out to be equal to 2A by RT minus V. This can be done if we know simple algebra rules. So if we use this in the definition of mu, we get mu equal to 1 by Cp 2A by RT minus B. So this is the expression for van der Waals, the Joule Thomson coefficient for a real gas. So if 2A by RT is going to be equal to B, then mu is going to be 0 and no change is observed in the temperature. So we can just rearrange this to have T equal to 2A by RB. So this is that inversion temperature which we talked about. And if the temperature initial is less than inversion temperature, we are going to see cooling effect, which is also the case when 2A by RT is greater than B, right? Because in that case mu is going to be positive. Or if the initial temperature is greater than the inversion temperature, we are going to see heating effect. That is when 2A by RT is smaller than B and mu is going to be negative in that case. So this explains all the possible outcomes of the Joule Thomson effect. So in order to achieve cooling, we must start with the temperature in the region 1 to be smaller than Ti, so that the temperature in the region 2 is lower than T1, so we get cooling, so T2 is less than T1. And if now this gas is again fed back in the region 1, and it is, if again it is, so it is just has to be a repetitive process. So we start with T1 less than Ti, we allow to pass it through to region 2 so that it gets cooled. Now this gas is again fed back in the region 1. So anyway, this already cooled gas has a temperature less than Ti. So when it passes through this porous plug, it is further cooled. So if this process is continued repeatedly, every time as the gas passes through this porous plug, we achieve cooling. And after a sufficient amount of time, this drop in temperature is very high. So when Joule Thomson effect is carried out, or the Joule Thomson process is carried out repeatedly for a large number of cycles, we get a sufficiently high drop in temperature, provided we start with an initial temperature T1 which is smaller than the inversion temperature for the given gas. Thank you.